Hello, in this video, I'd like to go over how to solve a ordinary differential equation using a numerical solver, such as the one in Mathematica. This is very useful for tackling problems that are not solvable, especially analytically. Take a look at this example problem on the left, the predator-prey model, which is actually a system of differential equations, both of which are nonlinear and indeed not solvable using analytic methods. We can tackle this problem using a numerical solver, and I'll show you on the right, where we will find the solution and graph it, even though the solution will be an interpolating function. I'll explain what that is after we do that. So we start by um, defining the equations. We could just call them EQ1. You can call them anything you want. You can even call them something like equation one. It's up to you. So let's call them EQ1 with an equal sign. So we have x prime of t. Notice that x and y are themselves both functions of t. And over here, we want to use um, the multiplication symbol to ensure that we're multiplying, ensure that Mathematica understands we're multiplying these functions of t. So um, over here, what we have is our both functions of t. So we have two dependent variables with one independent t. Okay, so that should be equation one. Let's define equation two. Make sure you're typing y prime of t, not y prime of x. Okay, so we have our two equations now. Over here in this specific example in the book, we're also given initial conditions to use. So that's going to be part of our system of equations. So we would type ND solve, and we're going to have three sets of parameters that we're going to be entering. Um, so in the first set over here, what we're going to be entering is the equations. Over here, we're going to be entering the variables, the dependent variables we're solving for, namely x and y. And then over here, we're going to enter the independent variable and an interval for interpolation. So over here, we're just going to enter EQ1 for the same and EQ2 for the equations. And then I will also type in the actual initial conditions as well as equations themselves. Okay. For the second set of parameters, we're going to enter um, the dependent variables. Okay. And then finally, we're going to say, let's solve for t going from 0 to, and then at this point, we're going to have to enter a value based on the particular differential equation, whatever it is we're modeling. Now, in this case, we're modeling the population of predators and prey. So they could be like wolves and deer, and basically over a certain period of time. Okay. Um, Now, if there's no information given about the time, you can just guess at this point. Usually something like this is measured over years or potentially over a set of months. So for the time being, let's just enter 10. But like I said, you can adjust this and change this to 100 or 1000, depending on the particular problem you're working on. All right, so uh, we have a solutions, but you notice that the solutions are not themselves regular functions. Instead, they are interpolating functions. Just really briefly, what interpolating functions are. Basically, instead of giving you a full-blown expression which represents what the function does, instead, interpolating function is a set of points that the curve of that function goes through. Um, However, it is more than that. It's not just a set of points. Every time you ask it to evaluate at a certain value, which we'll do in a bit, um, there's an algorithm which basically interpolates for you based on the points that you have. Um, and what you could do is, what it does for you is it estimates what the value of the function would be at that point that you're asking it. Um, there are all sorts of numerical methods that Mathematica uses for this, which goes beyond the scope of the course at the moment. All right, so how do we actually use these functions? Because we have two functions, x and y. So what we need to do is um, we need to tell Mathematica to assign, to make that assignment. And the most reliable way is to say, okay, we have the solution for x. By the way, one of the good idea which could have been would have been to assign SOL or solution or whatever you want to call it um, to the output of ND-solve. Okay, so that way, I just ran that again. When I enter solution, right, it gives me the two functions. Now, one more thing. Notice the funny way that it's outputting. Hopefully, you're already familiar with this. The functions are themselves kind of like assignments. So this itself is the function, and it's written in the form of an assignment. It says that x of t should be assigned to this function. And so this is actually there for a reason. The reason is that we can easily do a reassignment, which we're about to do. Um, so we're going to say, let's define x solution as a function of t. Okay. You need to enter the colon equal sign. And then you need to use the evaluate method here. So you want to say that we want Mathematica to evaluate x of t, where the first item on the list of solution is available. So if you look carefully, you have curly braces here. And you have two sets of curly braces. You have um, so you have a list inside a list. And what this first does is it pulls out the first item on that list, right? So just a second before I go ahead and evaluate that, let me show you. So if you type first solution, right? Um, so all it's doing is it's pulling out the first thing on that list. Notice that this one now has a um, single set of curly braces. Another way we could have done that is using the double bracket symbol like this. So what this does is it pulls out the first thing on the list. Okay. Now, it happens to be the case that this itself is a list and it has two items in it. And so if you want to pull out one of the items, what you could do is, again, you can use the symbol that pulls out the first item, as you can see, or we could have pulled out the second item, the y of t assignment, as you can see. So this second, like pulling out the inner item in the list is not necessary. We don't have to go through that. Um, but I just wanted to show you what this does, right? So going back to the evaluation, so we're saying let's assign x solution to this function where forward slash dot means plug in, right? We want to plug in the first thing on the list of solution. Okay. Evaluate is important so that it actually carries out, it actually serves as a function of t. Otherwise, it wouldn't serve as a function of t. All right. So looks like that's been recorded just fine because there's no response. And then we'll do the same thing here, where we'll do y of t this time, forward slash dot first, again, solution. So you don't have to do second, of course, because again, we're only pulling out the first thing on the list. All right, so we have our function, and once we have it, notice we can actually plug in any value we want. We can, in fact, even take the derivative of this function with respect to t um, at a specific value. not as an expression, but a specific value. So that's the only thing is that we don't get to have some sort of algebraic expression, but rather serves almost like a regular function in every other way, right? And finally, we can plot it, right? We can graph the function. So we can say, all right, let's plot the set of these functions, x sol of t and y solution of t. And at this point, we do need to remember that our interval was from 0 to 10, right? So that's because x solution and y solution are defined way over here, right? And on this interval, okay? All right. So you could see that whenever um, the uh, I don't remember which one was which, but you could see whenever one of the uh, characters goes up, one of these predators or prey goes up, the population goes up, the other one goes down, um, and vice versa. So you have this sort of symbiotic relationship between predator and prey from the original function, from the original differential equation. Okay, that concludes as far as like how to graph, how to do the problem in in the book. As you can see, it's very similar. In this case, we graphed only this first portion of the graph available in the book, but we could have easily gone from 10 to looks like if we were to use like 30, then we would get this full graph. Well, thank you for listening to my little tutorial.